Hello everyone, welcome back to thermodynamics subject. Today we are going to continue our discussion about closed systems. In previous session we have started to discuss about how we can consider how we can calculate the boundary work for closed systems. We use the knowledge which we got from chapter 1 to 3 to evaluate or to calculate the boundary work for closed systems. In this session, we will start to see how is the energy balance for a closed system. If you remember, in for closed systems, we had this equation, which you can see here for a closed system like this. For example, we have energy which come to the system which we call that E in, energy which goes out of the system, or E out, and a total change of the energy of the system, which the mm, difference between this energy input and energy output will be equal to the change in the energy of the system. And this energy which can come to the system or goes out of the system is not only actually the energy form, actually it can be work form as well. In other words, this E in minus E out is energy, net energy transfer by heat, work, or mass, which for a closed system, actually, we don't have mass transfer. So whole energy transfer for a closed system is due to heat as a Q and W as work. Uh, Change in the work of the system actually. And delta E systems, or change in the energy of the system, includes changing the internal energy, changing the kinetic energy of the system, changing the potential energies, and other types of the energies which we may have for a closed system. But usually in our discussions, in our calculation here, especially the rest of this session, we will see we usually can ignore kinetic and potential energy in our calculation, and whole change in the energy of a system or closed system. A closed system is due to change in the internal energy of that system. And this equation, you also, if you remember, we had in the rate form. In other words, the each one of these E in, E out, or delta E of the system per time will give us the uh, those terms in terms of time, and which we call that the energy balance equation in the rate form. So E dot in minus E dot out, or rate of energy transfer, the net energy transfer, and DE system per dt, or rate of change in the internal or uh, different types of energy per time. We had these two equations in previous chapters. And the total quantities which are related to this quantity per unit time uh, in the previous equation which we had here is something like this. For heat, heat, as I said, we show heat to the system, or from the system, as a Q, which can be Q in to the system, Q out goes out of the system. And the relationship between the rate of the heat transfer and mm, yeah, heat transfer can be shown by this equation. Q is equal to Q dot delta T. Q as a heat transfer or heat transfer, and Q dot heat transfer, rate of heat transfer actually. And delta T is the period of time which that heat transfer is happening during that process. Same for work, work rate or power actually, times delta T, or the time interval for that process will give us the W, or work of the system. And same for delta E of the system, which is dE divided by dt times the time for that process. And also by dividing this equation, which we had here, if we divide the terms in this equation to mass of the system, we will have the energy balance for that system per unit mass basis. So if we just divide this by m, we will have this equation, which is the energy balance per unit mass basis. E in minus E out equal to delta E of the system, but this lower form of the E shows that this is the energy balance or energy to the system per unit mass. And also we had energy balance in differential form, if you remember, and this is for energy balance for differential in differential form, the general one, and the energy balance in differential form per unit mass basis will be like this. Up to here we have already discussed in previous chapter, which was about the energy of the system actually. And for a cycle, like what you can see here, we call that cycle. If you remember cycle, the definition, according to definition for a cycle, the the system will go through different processes and it will go back to its initial state. We call whole this process as a cycle. So the system will go back to its initial state. Then for a closed system, actually, energy balance for a cycle actually will be like this. W net out will be equal Q net in, or W dot per unit time, or in term of in rate form actually, the energy balance equation for a cycle will be W dot net out minus Q dot net out. Why we have these equations? Because this term for a cycle will be 0. We don't have any change in the total energy. In other words, delta E of the system means E2 minus E1. For a cycle, E2 and E1 are identical. So delta E for a cycle will be 0. Then this delta E of the system, change in the internal energy for a cycle is 0. Then Q net will be equal to W net, or whole work which come to the system or goes out from the system will be equal to the work which is done by system or on the system. What is important here in this equation, as you can see here, we define according to the subscript we have written here Q net in. It means the heat is to the system. In other words, if this is closed system, heat is like this, and W is like this. Come to the system, goes out of the system work. Or work is done by system on surrounding. This is system, this is border or boundary actually, and other than that will be surrounding. So for this system, we imagine that energy which or the thermal energy or heat which come to the system has a positive sign, and the work which is done by system has a positive sign as well. This is just our assumption, which will help us for our calculation related to energy balance for a closed system actually, which is Q net and W net, or net heat transfer of the system, will be equal to the heat which come to the system minus heat which go out of the system. In other words, for a closed system, we may have some heat transfer from that system to surrounding, and also we may have some kind of heat transfer to the system from surrounding. Imagine we have such a pot or something, we have a heat source here. Then in the Q, we have Q in here. And also we have heat transfer from this. Imagine here we have water. We have also heat transfer from this system to surrounding. We have Q out. So you can see here the Q net will be differences between these two, Q in and Q out. The equation which we have here. Same for W net, which we have a piston here, a piston and cylinder. The movement of piston will produce uh, the movement of piston here will heat source again here. This piston will uh, move upward, and we have boundary work, if you remember from previous session, and which is work done by system or W out. And we may have a spring here which force this spring downward, which is work on the system. So we have W out and W in for this system. Then we need to calculate W net in, which is the difference between the W out and W in for that system. Here is just simple example to show this. So for a system, we need to calculate both of the W net and Q net, which this Q net and W net should be calculated according to the direction of the work and W for that system as well. So energy balance, when we are using these energy balance equations, actually, we need to have an assumption for direction of the heat and work. As I said, for a closed cycle, we don't have any mass transfer. So whole energy change of the system will be due to the work or heat which comes to the system or goes out of the system. Then we need to have an assumption for our calculation, like what we have here. Heat input and work output are positive. This is a very important assumption, and we need to consider this sentence or phrase in our assumption when we are going to solve an equation, any problem related to the closed system, especially. And also heat output and work input are negative. This is just our assumption for simplification of our calculation. And as you can see here, we have different forms of the first law relation or that energy balance equation for a closed system when sign convention is used. We call this sign convention. This sentence we call this sign convention. So the general form is like this: Q minus W equal to delta E. Or we imagine we have Q. When we are going to solve a problem, first we imagine we have Q to the system, positive sign, and W done by system and surrounding or negative sign. Or work on the system. So usually we imagine we have work to the system and Q from the system. Q minus W equal to delta E. And in form of for a stationary system, it will be Q minus W equal to delta E. Why? Because here delta E is a delta kinetic energy, delta potential energy, if you remember this equation, and delta U. The change in the energy of the system, according to what you have learned in chapter 3, is equal to change in the kinetic energy of the system, change in the potential energy of the system, and change in the internal energy of the system. Here U is the internal energy of the system. We have already discussed about that. And general form of this equation so will be like this: Q minus W equal to delta E. This is for a closed system, so we don't have mass. The change in the energy is only equal to change in the work and heat. And for a stationary systems, which we do not have kinetic energy and potential energy change for that system, whole change in the energy will be delta U, or whole change in the heat and work of the system will be equal to change in the internal energy of the system. And per unit mass, simply we divide this QW delta U by M, as similar to previous slide. We will have Q sub cube or sub W equal to delta E. And in the form of differential form, simply delta Q minus delta W for dE, or differential change in the energy of the system. So simply you can see different forms for energy balance equation for a closed system, general form for a stationary system which doesn't have any potential or kinetic energy changes per unit mass, and also the differential form for that system. You can see here what I told you. For a cycle, delta E will be equal to 0. Why? Because Q is equal to W. This is the first law for a closed system. The first law cannot be proven, actually, as it is written here as well. We cannot prove the first law. We don't have any method to prove that. But up to now, it has not been anything which can be against the first law of thermodynamics or conservation of the energy. As you can see here, we have discussed. So we use this conservation of energy as our role here to calculate the change in the energy, or to write the energy balance actually for a closed system. Now we will see in an example how we can use those equations to find the change in the energy for a closed system. In this example, we have a cylinder piston or piston cylinder as usual to have a better understanding about closed system. A piston cylinder device contains 25 grams of saturated water vapor. So this is important information about its initial state. It contains 25 grams of saturated water vapor. That is maintained at the constant pressure of 300 kilopascal. So the pressure for the process will be constant. We have constant pressure process. Initial pressure is 300 kilopascal, and final pressure also will be 300 kilopascal. P1 is equal to P2. A resistant heater within the cylinder is turned on and passes a current of 0.2 ampere for 5 minutes from a 120 volt source. So we have a wire or a heater actually here inside which goes inside the piston cylinder device, and also we have the current, voltage, and also the time and duration for this current which goes through this wire to the cycle. In other words, we have WE, or the work, electrical work to the system. And as you can see also in this figure, we define the boundary like this, or the saturated with water vapor as our system here. And as you can see here, we have a closed system. We don't have any mass transfer between these. This is the guide for us. We don't have any mass transfer between this system which we have selected, this system, and surrounding. So this is a closed system. What we have is work which comes from this wire or electrical work to the system, which system is the saturated water vapor, as I said. and we know how much is the mass of that. We know the P1, P2, or the pressure during whole process will be constant 300 kilopascal. So what is the process actually here? Here at the same time a heat loss of 3.7 kilojoule occurs. So we have Q out of the system, heat loss from the system, which is 3.7 kilojoule from the system to surrounding. In other words, during 5 minutes, we have this work, WE, to the system. We have a transfer Q out equal to 3.7 kilojoule from the system. WQ we have for the system during those 5 minutes. So we have a heat transfer and the work to the system during 5 minutes. Now we are going to calculate or determine. First, we need to show that for a closed system like what we have here, boundary work or WB and the change in the internal energy or delta U. U is internal energy, delta U is changing the internal energy. In the first law relation can be combined into one term as delta H. If you remember, we have already introduced H as enthalpy, which is combined characteristics or combined properties of a system, H or enthalpy of the system for a constant pressure process. So in part A of the question, we are going to show that the boundary work for such a closed system is directly related to the delta H or enthalpy of the system instead of using delta U. And in part B, we need to determine the final temperature of the system, of the steam, which we have in our system, or T2N. First, let's see what we have. We have saturated water vapor in a piston cylinder device. It expands and constant pressure. Why it expands? Because we have this work on the system, so it will increase the energy of the system. When the energy of the system increase, it means also the temperature will change, and then volume will change. And because this piston can move, in other words, there is a hint. We have a constant pressure process. In other words, we don't have any resistance for movement of this piston. If it was not a constant pressure process, means this piston should be fixed. And work which comes to the system will increase the, try to increase or expand the gas, which is water vapor here, but due to the resistance, it will increase the pressure. But here, pressure is constant. It means we have expansion for our system, which is due to the heating. It is to be shown that we have delta U plus WB equal to delta H according to part A of the question. And also we need to find out temperature of the steam here. Let's start with assumption. Please, if anytime you want to go to answer to any problem related to thermodynamics especially, write the assumptions. These assumptions are important. Without this assumption, your calculation is useless because we don't know in which condition your calculations are valid. There is numerous conditions that make your calculation not be valid for that system. So you need to define your assumption if you need to write those assumptions to be used or to use different equations, for example, in your solution. The first assumption is the tank is stationary and thus the kinetic and potential energy changes are zero. This is important because we are going to remove this part, delta KE and delta PE. We don't have any information for the potential and kinetic energy of the system. So we can imagine that the Even for a closed system, we may have delta KE and delta PE. But here, because system is stationary, its elevation doesn't change the system which we have here, and also it doesn't move. If you remember for delta P and delta K in previous sessions, we can calculate them for delta K for a system which is moving, delta P for a system which its elevation actually changed. But here, everything for our system, which is the steam here. The system here is water vapor. So delta P and delta Ke, we assume they are zero because we have a stationary system. Therefore, delta E will be equal to delta U. If you remember in the equation which I show you here, we have a stationary system, so delta E will be equal to delta U only. And internal energy is the only form of energy of the system which may change during this process. Assumption number 2, we have electrical wire which constitute a very small part of the system. Here in our system, which we select, we have also this wire, which presence of this wire inside this our system may be effective on the properties of the system. And to be too much specific and accurate, we need to consider this wire as well, its properties, which may be different from the steam. But here, because this wire is just small part of the system, we can ignore the energy change of the wire. In other words, we imagine the change is only, we assume that the change in the energy of the system which we have selected is due to the change in the internal energy of the water vapor or steam here. As I said, according to how in analysis, I will just repeat what I told you up to now. We take content of cylinder, including the resistant wire, like what we have here as our system. This is a closed system with the reasons which I told you, no mass transfer. And we observe that a piston cylinder device typically involves moving boundary. This is moving boundary. It will move, and we will have a boundary work. We have discussed in previous session about that. The pressure remains constant during the process according to question instruction P2 equal to P1. And also it is lost from the system, and the electrical work or WE is done on the system. This is the information which we have for our system. For the first part of the system, we can, for a closed system, when we are going to see how is the energy balance or the how is the change in the energy of the system in thermodynamics, we need to write energy balance equation for that. This is a general equation, E in minus E out equal to delta E of the system, which already I have discussed about this equation. So this equation will be Q minus W equal to delta U plus delta KE plus delta PE. We already discussed about this. Delta E, or change in the energy system, can be changing due to the change in the potential energy of the system, or kinetic energy of the system, or internal energy of the system. Here we have a stationary system, so delta PE, delta KE are zero. We have only delta U for the system. How about E in minus E out, or energy to the system, or energy goes out from the system? As we discussed earlier, we need to have assumption for the direction of the work and the heat from or to the system. Here, as I discussed earlier, we select the direction of heat transfer to be to the system and work to be done by the system. So the sign for Q will be positive because we have Q to the system. This is just assumption. Here, however, we have something like this. Q out goes out of the system, but we can have our assumption later. We will see if our assumption is right or wrong for this system. So we assume that Q is Q is to the system and work be done by the system. So Q minus W, positive sign for Q, negative sign for and both of them actually are positive. We initially assume both of them are positive according to what we had here. Heat input and work output are positive. Okay, simply we have Q positive, W positive. So according to this equation, we have Q minus W. And we assume the work which we have for the system is boundary work and also W other. Here we do not include the work from uh, electrical wire. Later we will discuss about that. We assume we have boundary work and other types of work. So we express the work as the sum of boundary and other forms of work such as electrical and shaft and so on. Any types of the work can be. This is a general equation actually for a piston cylinder, which includes a work input for the system or output of the system actually. So we need to write like this: Q minus W other minus this W actually is equal to W other plus WB. If we substitute this W other and WB here, Q minus W other minus boundary work will be equal to U2, this is delta U, U2 minus U1. And as you have seen already in previous examples, for a constant pressure process, the boundary work will be like this. WB or boundary work for a constant pressure process like what we have here will be equal to P, which is constant, time change in the volume of that system. So if we just substitute this here, WB in this equation, we will have this equation Q minus W other minus P 0 or P, which is constant here, times V2 minus V1 equal to U2 plus V1. So simply we can reach this equation by this information: constant pressure process and boundary work for that process. And we have already discussed that pressure in state 1 and state 2 are identical, like as P1 equal to P2 as P0, which we have here. So we can rewrite this equation like this: Q minus W other equal to U2 plus P2 V2 minus U1 plus P1 V1. We can simply write this equation. If you notice here, this will be P2 V2 here. P0 can be 1, P1 V1. And if we both of them are negative, if we bring the other side actually will be positive, and we can have this equation U2 plus P2 V2 minus U1 plus P1 V1. So simply we can reach this equation, the following equation, which is the we can reach this equation according to the information which we have for this closed system in a constant pressure process. And if you remember, for enthalpy or H, we had this equation H equal to U plus PV, or we can find H as the combined properties of a system by if we know the internal energy of the system, and also pressure and volume of that. So if you notice here, this will be H2, this will be H1. So Q minus W other will be equal to H2 minus H1. Simply the change in the uh, energy of the system can be found by, if we just know the change in the enthalpy of the system. So for a constant pressure uh, process, we need to just know the enthalpy of the system, or change in the enthalpy of the system. This equation is very convenient to use in analysis of the closed system undergoing a constant pressure quasi-equilibrium process, which is a common form of the process actually for closed systems. So in many cases, we can just use this equation instead of this one. Instead of we find U2, U1, and also P1 and V1, we simply can use enthalpy of the system for a constant pressure quasi-equilibrium process. And as you can see here, we ignore boundary work. Our boundary work is automatically considered in the enthalpy, or change in the enthalpy of the system. So we don't need to calculate the boundary work and internal energy of the system. We can combine them, and simply we can use just enthalpy. Here we will see how it can be used. This part we finished part A of the question. We found this equation and we proved that the enthalpy of the system will give us the change in the energy of the system actually. In part B, we are going to find the final temperature of the steam in this process. Now, according to the equation which we have here, we have Q actually, it is given. And for H2 and H1, we can go to the table and find them according to the properties which we have. We'll see later. But we have also W other. W other here, other than boundary work, is electrical work, or WE, which we have already seen in previous chapter, chapter 2 actually. WE is equal to VI delta T, voltage, current, and time interval, which we have all of those information: 120 volts, zero point 0.2 ampere, and delta T was 5 minutes, which means 300 seconds. And this unity conversion, and finally we will have work, uh, electrical work to the system equal to 7.2 kilojoule. And so to use this equation, we have this W other. Now let's see how we can find H2, or enthalpy at state 2, enthalpy in state 1. In state 1, we know how much is the pressure, 300 kilopascal, constant pressure. Also, it was mentioned that we have saturated water vapor. So here we have this information: pressure and saturated vapor. It means enthalpy at state 1 is saturated enthalpy, or Hg. We need to go to the table A5. You have already familiar to use that table. You need to go to the table A5 and find enthalpy for saturated water vapor in this pressure, which is the simple way to find the enthalpy. And at final state, the enthalpy can be determined directly from this equation 418. Why we are going to determine This enthalpy here, if you notice, we have W, we have Q, it was mentioned, 3.7. We have H1. Now we need to calculate H2. And if we have H2 as enthalpy of the system, we have pressure as well. So we have P2, then we will have H2 as well. We have P2 and H2 for steam. We need to go to the table related to that steam in that pressure and that enthalpy, and we can find temperature for that state from the table. So let's first find H2. And before we use that equation, up to here we have assumed a direction for the W and Q. Let's see what are those assumptions and how we can use those assumptions to find H2. By expressing transfer from the system and work done on the system as negative quantity. These are our assumptions here. We express heat transfer from the system and work done on the system as negative quantity. So we have 3.7 kilojoule negative sign, and also we have work on the system, which is also negative sign. So again, we can write this E in minus E out, delta E system energy balance equation. WE, here, this equation, delta U is simple. We have already discussed delta is equal to delta P, E, delta K, E, delta U, 0, 0. We have only delta U, simple. W, and also we have here Q and W. But here also we have some assumption for those. We have assumed that we have uh, WB and W other, which we have calculated W other as WE or electrical work. We here the initial form is like this, Q minus W, but here we say that the heat transfer from the system and work done on the system are negative. So this will be like this because we have Q out minus Q uh, uh, minus W also is negative uh, on the system actually. So minus WE, and WB is from the system actually. This is due to movement of the, so boundary work is under by the system. So plus WB. In this equation, if you notice, here will be like this. This is negative. This will be positive. WE minus Q minus WB, like what we have here. WB, work done by system and surrounding. Q out or Q which goes out from the system to surrounding, negative sign, negative Q out, and WE in, which is work done on the system, again negative sign, but if we put here, it will be positive here. However, generally we need to put in this equation as a general form. This is, as I discussed, sign convention. So we usually use this equation and these assumption. Otherwise, we need to state them. And we have already found here WE in minus Q out will be delta H. If you remember, if we just simply W in minus Q, if you bring WB here, WE in minus Q out is the equation, and delta U plus WB. But we have already proved here that this boundary work can be included in the change in the enthalpy of the system. So instead of delta U plus WB, we can write delta H of the system. And as you know, delta H of the system, or capital H, will be, this is specific enthalpy. So M times H2 minus H1. This is H2 minus H1 actually. This is this one, but we need to use a specific one because later we will go to the tables to find this enthalpy. And if you go to the table, this enthalpy is given according to the in terms of a specific enthalpy. So delta H equal to mH2 minus H1. We have also M for the steam or water here. So delta H equal to M sub H2 minus H1. And we have all of this information. We have WE in, we have already calculated. We have Q. We have M. We need to use convert it to kilogram from gram. 25 gram convert to kilogram would be 0.025. Kilogram times H2 we don't have, and we have H1 as well from table, which we have already found it. Then according to this equation we can find H2. So for state 2 we have H2 or enthalpy in state 2, and also we have P2, the pressure. By this information we can go to table A6 and find temperature for this. If we have directly this temperature for this pressure and this enthalpy, it's okay. Simply we can find it. Otherwise, we need to use interpolation to find this temperature, which we have already discussed in previous chapter. How you can do interpolation. I'm not going to go to the details for interpolation or to find this information from the table. Simply, if you go to table A6 for this pressure and this enthalpy, directly or by interpolation, you can find this temperature. So the final temperature of the water vapor here will be 200 degrees Celsius. So steam will be at 200 degrees Celsius. Here also, up to here, the question is finished. We have reached all of the answers which was required for the question. But here we have more explanation, discussion, extra information actually according to the example which we have here. Here, if you notice, we introduced this system as a stationary system. In assumption, we said that the potential energy, the change in the potential energy is zero for this system, which is the steam or water vapor here. But to be more specific, when when this piston goes up or move upward, this system will change as well like this. And we have new system, new boundary. In other words, this system has a change in the center of mass for that. The initial system center of mass is here. When we have expansion, imagine this is system, its center of mass will be here. So we have a change in the center of mass of the system. In other words, we have a change in the potential energy of the system. So delta PE generally, to be more specific, is not 0. But even we include this, and if we notice that the center of mass is changed uh, equal to 1 meter, which is actually exaggerated assumption. If we imagine this piston will goes up 1 meter and the center of mass position of center of mass is changed uh, equal to 1 meter, then uh, the change in the potential energy for the steam will be 0.0002 kilojoule, which you can see here. Uh, here the work which we have for electrical is 7.2 kilojoule. So you can see how much is small this change in the potential energy. And our assumption just cause very small error for the result which we can get from such imaginary uh, system. So according to this explanation, you can see we can always neglect the potential energy for such a system, which includes uh, piston, cylinder for a closed system or uh, for a closed system. Actually. And we will see in next example also how we can use this energy balance equation for a closed system. Here we have an interesting example for a closed system, and we'll use most of the information which we have learned up to now from thermodynamics. We have on a restrained expansion of water. We'll see what is an restrained expansion of water actually. We have a rigid tank, like what you can see in this figure. Rigid tank means uh, the boundary or the border of that tank will not change. So the volume of the tank will not change. We have divided this tank to two equal parts. Initially, we have water in one part of this rigid tank, as you can see here, and we have evacuated uh, the other side. So we have a space here, which nothing is there actually. The initial temperature of the water here when we have this partition is 25 degrees Celsius. Its pressure is 200 kilopascal, and the mass of the water in this part is 5 kilograms. Then we remove this partition actually, and water can occupy actually whole space, and we will give enough time to the tank or to the water to reach a stability with the surrounding, to reach the, the temperature of 25 degrees Celsius again, which is its initial temperature. So after we remove this partition, we remove this partition, then water will be in whole these rigid tanks. But we know how much is its temperature, 25 degrees Celsius. How about pressure? We don't know. We know its initial pressure, but when we remove this, the pressure will change for sure. And also we have heat transfer between this tank and surrounding. And according to the system which we select here, volume can change or can be fixed. Let's see first what we need to find for this in this example. We need to find the volume of the tank. How much is the volume of the tank? How much is the final pressure inside the tank. And also we need to calculate the heat transfer for this process. The process here is when we remove that partition from the rigid tank. This example is a good example to show how much selection of the system is effective on our result. What can be the boundary or system here actually? The boundary which we select here, or the system which we select here, is like this. We select whole tank, includes the water and evacuated space as our system. So the boundary will be like this red dash line, and according to this system which we select, we will have a constant volume process actually. So whole volume of the process doesn't change during the process. However, the volume of the uh, water will change for sure, or maybe change. We need to calculate. So this is what we have. We have one half of a rigid tank, which is filled with liquid water, while other side is evacuated. The partition between two parts is removed, and water is allowed to expand until fill the entire tank, while the temperature is maintained constant. The volume of the tank, the final pressure, and the heat transfer need to be determined. Let's see what should be our assumption. As usual, we need to uh, think about the. Now here we have that heat transfer. We need to calculate heat transfer. In other words, we need to we need to use that energy balance to find that heat transfer. So to use that energy balance first, we need to see if the system is stationary or not. How or which type of energy have in our system. And also, if you notice here, this system, according to the dashed line, is a closed system. Why? Because we do not have any mass transfer to the or from the system, or m is equal to 0, or m dot actually. So the system is stationary, and thus the kinetic and potential energy changes will be 0, and delta E will be equal to delta U, or the change in the energy of the system here will be equal to change of the internal energy of the water inside the dashed line. The direction of its transfer is to the system. So this is our imagination. We imagine the system during this process, this expansion of the water will absorb temperature, or we have heat gain, or Q in. A negative result for Q in indicates that the assumed direction is wrong, and thus it is heat loss. So first we assume a direction for Q. Finally, we will find a value for Q. If it is in a positive sign, it means the direction which we have selected for Q is okay. Otherwise, uh, the assumption for the direction uh, had been wrong, and we have, instead of heat gain for the system, we have heat loss from the system. The third assumption is the volume of the rigid tank is constant according to the question. Also, we can see that, and thus there is no energy transfer as boundary work. If you notice here, we don't have any boundary work. And there is no electrical shaft or any other kind of work involved as well, as you can see according to example or question instruction. We can have this assumption. Then we can, as I said, we can select the system like this. This is a closed system. No mass cross the system boundary during this process. We observe that water will fill the entire tank when operated, when this partition removed. We don't know if we remove this partition, the water will evaporate or not. We have what we have here. First of all, we need to check what we have in initial state. It is 100% liquid water, or in other words, we have a compressed liquid here, or we have a mixture. How we can understand that? According to the information which we have. P1 is 200 kilopascal and T1 is 25 kilopascal. If you go to the table, different tables which we have, like table A5, water in tank exists as compressed liquid. Why? Because its pressure, 200 kilopascal, is much greater than the saturation pressure at 25 degrees Celsius. So it means that what we have here in initial state is compressed liquid. We don't have any mixture here, and we don't have saturated liquid as well. We have compressed liquid in this state. So we can approximate, and by approximation, we can use the properties of the saturated liquid for water. If you remember, we had this assumption when we have a compressed liquid, we can use uh, saturated the properties of water for saturated liquid. In other words, we can find a specific value for uh, water at its initial state. In initial state, we have water with 25 degrees Celsius and 200 kilopascal. You can go to the compressed liquid and find the specific volume, but you can also go to the table A4 and find VF, or a specific volume for saturated liquid at 25 degrees Celsius, which is equal to this. So you can find a specific volume from table and the information which we have for initial state. Then the volume of the water in initial state will be like this: V1 equal to MV1, which is, this is volume, this is a specific volume. And M also is the mass of the water which we have here. It is 5 kilograms. Simply, we can calculate the initial volume of the water. But what we are looking for is whole volume of the tank. We have calculated the volume of the water at initial state. As I said, the volume of the tank, the tank is divided to two equal space actually. So when we have this, the volume of the tank will be 2 times the volume of the liquid or of water here, which we have in one partition of the tank. So V tank will be equal to 2 times this. This is volume of the water, or volume of this portion. V tank 2 times this will be 0.01 meter cubed. So we have calculated the volume of the tank. At part B, we are going to find P2, or final pressure in the tank. How we can reach that? First, we calculate a specific volume for the final state. According to volume, which we have calculated here, and mass, which we have, V2, or a specific volume for state 2, will be this much, or 0.002 meter cube per kilogram. And it is which is twice twice the initial value of a specific volume. It is reasonable because the volume is doubled actually, and at we also know how much is the temperature. So we have temperature 25 degrees Celsius. We have calculated V to our specific volume per kilogram. So we have seen different examples like this. We need to understand what is the phase of water with these characteristics. How we can find that? We have temperature of the water. So we go to the table A4. And we need to find Vf and Vg for this temperature. Then we need to compare V2 with Vf and Vg. If V2 is higher than Vf, we have superheated vapor. If V2 is lower than if V2 is higher than Vg, we have superheated vapor. If V2 is lower than Vf, it means we have a compressed liquid. And if V2 is between Vf and Vg at 25 degrees Celsius, these Vf and Vg should find in table A4, which we have already found them. And our V2 is, if you notice here, our V2 is between these two. So we have a saturated mixture, saturated liquid vapor mixture. And if you remember for this phase, the pressure will be saturated, should be actually saturated pressure. So P2 is saturated pressure for of water at 25 degrees Celsius, which also we can find from the table. So the final pressure also will be 3.1698 kilopascal. So here you can see simply we can find final pressure as part C is a little more complex than part A and B. In this part, we are going to calculate the heat transfer of the system which we have selected. And to do this, we need to use that energy balance equation, A in minus E out equal to delta E of the system. Which what we have here is Q in equal to delta U. In other words, here, according to what we have selected here, we do not have any work in our system. No movement, no boundary work, nothing. So we have only heat transfer, Q in equal to delta U, which this is the internal energy, and internal energy will be like this. This is specific internal energy times mass of the system. So we can write this is delta U is U2 minus U1 or MU2 minus MU1 or MU2 minus U1. Very simple and easy. Q in equal to MU2 minus U1. Here we have Q. Here we don't have Q actually. We are going to find Q, but we have M. And also, so we need to have, let's see if we have U2 and U1. or internal energy of the system or water uh, mm, here in our or the water. Actually, what we have in our system is only water, because in initial state this part is evacuated. Final state, this part is filled with the water. So in initial state we have for the system we have uh, compressed liquid of water and evacuated space actually, or only compressed liquid, and in final state we have saturated vapor and vapor water mixture. So we can find U2 and U1 for that. For U1, as we discussed, we have saturated water, and we can use this equation. U1 equal to UF at 25 degrees Celsius. Simply from table A4, we can find this U. So we have U1 as well. How about U2? U2 in the mixture region. If you remember, for mixture region, we have quality. How much of the mixture is vapor? How much of that is uh, water or liquid? First, we need to calculate x. Actually, the equation we need to use is this one. U2 is equal to UF plus x2 UFG. UF and UFG are for temperature of the water, internal energy of the water, or saturated internal energy, or internal energy for saturated water at 25 degrees Celsius. UFG is the internal energy for saturated mixture actually. What we don't have here is X2. Both of these can be found from table, but we don't have X2. How we can find this X2? First, we need to calculate it by the information which we have. And we can use this equation, x2 equal to V2 minus Vf divided by Vfg. We had this equation in previous chapter, so the quality of the mixture x2 will be equal to V2 minus Vf divided by Vfg. We have Vfg for 25 degrees Celsius, constant temperature process we have here, and V2 we have calculated in previous step. We have calculated V2, so we have V2, we have Vf from table, and Vfg. Simply we can find Vfg. We can like this, Vf minus Vg. Simply we can find it. Then x2 will be this much. By substitution of x2 in this equation, we have Uf from table, substitute x in this equation, we have UFG from table, and finally we can calculate U2, or internal energy of the system at the final state. By substitution of U2, U1, and M in this equation, Q in will be equal to this much, 0.25 kilojoule. And so the heat transfer from the of the system actually, the heat transfer of the system is 0.25 kilojoule. And if you notice here, the sign of the Q in here is positive. It means our assumption about the direction of the Q in was correct, and we have Q in to the system. Direction of the transfer is to the system, and system is heat gain system actually. This is what I told you. So in this example, you have seen how we can use all of those information which we have learned up to now. Comprehensive example actually, and very important example. Just one thing about the system which we have selected here. If we just select this part as our system, we couldn't solve this equation actually easily, because we could not include the other part, and we couldn't uh, calculate the boundary work here as. So by this, we reached the end of this session. I would like to say thank you for watching this video lecture. See you next time.